And the next talk is by Charlet, the impact of thermal radiative losses on microquasar jets. Go ahead, please. At the moment, we don't hear you. Can you say something? We do not hear you.
Check. Oh, yeah.
No, we still don't hear you.
Okay, maybe like that.
Now we hear you, yes.
Yes, sorry, was up here. Okay, let me share my screen. Up here, share. As soon as it works, wait. Here it is. Up. Do you see?
Yes, it works.
Okay. So first of all, thank you for letting me present my results. I'm Arthur Charlet. I'm a PhD student with Rolf Walder at the Charlet Impact and Alexandre Markovit at the Olympium Montpellier. And I will talk to you about thermal radiative losses in high-mass microquasar jets, which is my subject on PhD thesis. So first of all, I don't think I have to present the context of high-mass microquasar jets. So those jets that we see due to the radiative processes, my question for my PhD thesis was, does these processes have an impact on the evolution and the structure of those jets? So for this, we perform large-scale and long simulations over long times with a three-dimensional relativistic hydrodynamical code with those thermal radiative losses that we derive. So for that, we chose to simulate two systems, Cygnus X-1 and Cygnus X-3, Cygnus X-1 being one of the most observed and well-known high-mass microquasar system. And we chose to focus also on Cygnus X-3 due to its characteristics, because by being more compact, with a stronger wind, a star is hotter, and so on. With all those characteristics, we expect stronger losses with our framework, within our framework. So the methods we use perform simulations with the Maze toolkit from Walder and Follini, which solves the relativistic equation on an Eulerian grid. So we added a loss term on the energy equation. And as far as I know, we're the first simulations of high-mass relativistic jets, which are both relativistic and over large scale, and also the first implementation of radiative loss effects in the jet dynamics. So for the radiative losses implemented, we added free mechanism, synchrotron, and inverse quantum that I derived from the Maxwellian distribution for the electrons, and the line recombination that is active at low temperatures. On the right, you can see the evolution of those losses with temperature. You see the line recombination being stronger at a low temperature as expected, and free and inverse quantum scattering dominating at higher temperatures. So here are some results for our Fiducial runs. On top, you can see rest mass density slices for our Cygnus X-3 runs, and on bottom left, rest mass density slices for Cygnus X-1 runs. Both of those jets are supersonic jets according to the Martin 97 classifications. So we separate them in three zones: the beam, the inner cocoon, and the outer cocoon. So inner cocoon is made of shocked jet material, and the outer cocoon of shocked ambient material. We identify those zones with our post-processing code, and most of our results are based on this identification. So the evolution and the dynamics of the jets that you can see on the speed plots on the middle are separated in three phases, which are linked to the development of the Kelvin-Helmholtz instability. At first, there's baconical shocks in the beam that you can see developing as early as the first phases. Then it causes oscillations at the beam head, which causes oscillation in the speed diagram, and then these oscillations trigger mixing of the jet with the cocoon. So we performed a parametric study around those simulations. I won't be presenting all my results. I will invite you to read my papers that will, I hope, soon be published. It is actually in the reviewing process. So here you can see the effects of modifying the injected beam temperature from 10⁻⁷ Kelvin to 10⁻⁹. You see from 10⁸ and 10⁷, there's very few differences until the middle of the second phase. But there's a big difference when we raise the temperature to 10⁻⁹ Kelvin. There's a threshold effect and a strong destabilization of the beam. You can also see we draw the partition density function for those three jets at two different times, one during the second phase and one during the third phase. And we observe mainly two temperature peaks due to the beam and the inner cocoon. And so we may expect consequences in the emission signature maybe for those jets. Other results from this parametric study varying the jet density and wind speed. On blue, you can see the jet with the injected density divided by 10 for Cygnus X-1. We see the jet has a completely different dynamics due from the beam being bent away from the start and breaking earlier due to instabilities, which is in line with results from previous studies of the interaction of the stellar wind with high mass microquasar jets. And in green, so you can see the effect of accelerating the speed of the wind, stellar wind by 50%. So the instability grows very differently, as you can see in the speed diagrams, which shows a very different behavior in the second phase and less stable beam. So back to our main results, which are the cooling effects. So first of all, we observe barely to no effects on our similar Cygnus X-1 runs. Therefore, I'll be focusing on Cygnus X-3 runs to present those effects. So on the left, you can see temperature slices for the cool jet on top and the non-cool jet on the bottom. And you see visually differences in the structure, so mainly in the cocoon and the beam. The outer cocoon and the beam, which are different. And on the dynamical variables, you can see the cool jets being slower and mainly the less stable with a longer onset of the Kelvin most instability. Other effects, so we also just to look at the volume of each zone, as I told earlier. We see that at some point the expansion becomes self-similar past the binary scale. The evolution of the different zones are different. For the outer cocoon, the cooled outer cocoon is smaller in that the non-cool counterpart, but evolves with the same law. The inner cocoon shows a slightly stronger slope in the non-cool case, but the beam show vastly different behavior between the cooled and the non-cooled case. We explain those due to the structure of the beam. You can see on the left slices of the tracer density, which separates the beam material to jet material to the ambient material. And you see at the same point that the cool jet on top shows stronger baroconical shocks, which translate into a faster growth of the Kelvin-Helmholtz instability. We explain those stronger baroconical shocks and those structure due to a higher overpressure of the cocoon over the beam on the right. So for that, we use the volume average values from our post-processing of the simulations and to derive the pressure of each zone. And we explain this difference in this overpressure due to the effects of the cooling. Here we calculate for each cell of each zone the cooling for some points of our runs. And we see the cooling being dominated here by the free mechanism and being stronger in the beam than in the inner cocoon, which translates into a colder beam and therefore a stronger overpressure of the inner cocoon to the beam, which then explain all the structures and the dynamical differences I presented just earlier. So to conclude, we performed the first large-scale relativistic study of cooling in high-mass microquasar jet outbreaks. We observed weak tunnel effects on Cygnus X-1, but strong structural and dynamical modifications for Cygnus X-3. We also studied the parameter dependence of various quantities and dynamical or not over the for these jets. More on that in my papers that I hope will be published. For the prospects, we'll be letting our jets evolve further to study the steady state structure, which can be more related to observations. And we'll be also computing total synthetic thermal and non-thermal emission spectra, which we have also already preliminary results, but I won't be presenting them because they are still very preliminary. Thanks for your attention.
Thank you very much. Are there questions? Andrzej was first.
Yes, I understand that you assume that the jet is thermal at high temperature. And what sets the temperature, and why do you assume that the jet to have this temperatures? I'm quite confused about it.
What do you mean? I assume this temperature. How did I choose the values for our parameters, for the injection parameters? You mean?
No, I mean that usually we in those systems we see radio emission from power law electrons. So we believe we have initially magnetic jet and then acceleration of electrons, and the jets are rather not at all thermal in my view.
Yeah, but they're still thermal. I mean, we often talk about being a population of both thermal and non-thermal electrons in jets, and the non-thermal are the ones that dominate the emission. But we assess for over the scale of the dynamical conclusion of for the effects on the dynamics. The non-thermal electrons represent a small portion of the energy budget of the jets, since most of it are in the internal energy, and we also observe the effects of just the plasma processes, classical plasma, thermal processes, plasma processes on the energy budget of the jet for its dynamics mainly.
Okay, thank you. Ilyak has a quick question, I hope, with a quick answer.
Hi, Arthur. Nice simulations. I had a question concerning, so you say that in the prospect you are going to look at the thermal, the emission itself. In Cygnus X-3, like the compact object is deeply buried in the wind, which is radiatively driven. So that would be interesting maybe to study the radiative feedback on the wind structure. Did you consider this type of aspects?
No, but that's really a good suggestion, and I will try to think of a way to implement that.
Okay, thanks.
Thank you very much, and let's thank the speaker again, please.